So this chapter is all about the multivariate normal distribution. So we'll start by introducing the multivariate normal, then we'll talk about some distributions that derive from it, such as the Wishart distribution and Hotelling's t-squared distribution, and then finally we'll talk about how to do hypothesis tests based around the multivariate normal distribution. So with a standard univariate normal distribution, let's suppose we've got a variable x, let's suppose it's normally distributed, then the distribution is fully specified by its mean and its variance. X is distributed with normal, mean mu, variance sigma squared. Okay. And the density of x here will be f of x, which is just 1 over root 2 pi sigma squared, e to the minus x minus mu all squared over 2 sigma squared. So the multivariate normal is similar. Okay. Now, instead of having a scalar quantity, we've got a vector quantity. So let's suppose x is in Rp. And we'll write things like x has a multivariate normal distribution, and we'll now put a subscript p on here to indicate it's p dimensions. Instead of having a scalar mean, it's going to have a vector mean. And instead of having a scalar variance sigma, it's going to have a variance matrix, which I'm going to usually call capital sigma. Okay? So mu here is in Rp. This is its mean vector. So this is the expected value of x, and the variance of x, well, that's sigma, and that is a p by p matrix. This is the covariance matrix. Now its probability density function, this is its PDF in this univariate case, probability density function in this case is very similar as well. So f of x, well, we still get 1 over something at the start. We're still going to have a 2 pi. But now, instead of sigma squared, we get the matrix sigma. And we have to take the determinant of that. And then square root it. Okay. Times by, and I can't fit it all on one line here, so I'll split it. Times by e to minus a half. And we're going to do the same thing as we did for the univariate case. We're going to have x, the vector x, minus its mean. Now, we can't really square this anymore. It doesn't make sense to square it. So we're going to do the equivalent. So it's transposed, divide by the variance. So instead of dividing by sigma squared, we times by the inverse, like dividing by something. Yep. So the inverse of sigma times x minus mu. Okay, so this here indicates it's the determinant. So just note, again, that just like in the univariate case, the multivariate normal is completely determined by its mean vector and its covariance matrix, sigma. Okay, and we say that x has a multivariate normal distribution, which I'm going to abbreviate to MVN, has a multivariate normal distribution if and only if A transposed x is a univariate normal random variable for any constant vector A in Rp. So x has a multivariate normal distribution if and only if all linear combinations of it are univariate normal. Okay. This is a linear combination of the elements of x. So note that if we let A, say, be 1, 0, 0, 0, then A transposed x is just the first component of x, x1. So that must be normal with some mean and some variance, which I won't write in. Okay. So if x is a multivariate normal, then the components in x are all univariate normal random variables. And let's have one example. Let's have sigma to be a diagonal matrix, a covariance matrix. It's sigma 1 squared up to sigma p squared. Okay. Then we know that the determinant of sigma is just the product of all these terms. So it's going to be the product of sigma I squared, I equals 1 up to p. And that sigma inverse is going to be the diagonal matrix with 1 over sigma 1 squared up to 1 over sigma p squared. And the density in this case is going to simplify. We're going to have the density of x. Well, we said it's 1 over 2 pi times sigma squared. So if we multiply sigma by 2 pi, we're going to get 2 pi to the factor p here, times the product of the sigma I squared times e to the minus a half x minus mu transpose sigma inverse x minus mu. So this is going to be 1 over 2 pi to p product sigma I squared. Sorry, I forgot the square root before, didn't I? So it's the square root of all this. So p over 2 product of the sigma i's e, and then here we're just going to get minus a half the sum of xi minus mu I squared over sigma I squared. And this is just the product from I equals 1 up to p of 1 over the square root of 2 pi sigma I squared e to the minus a half xi minus mu I squared over sigma I squared. So in this case, the components of x are independent. They're independent because their PDF factorizes. The joint distribution of all the components of x factorizes into the product of individual PDFs, so they must be independent. Okay. So we have that the xi are normal with mean mu I and variance sigma I squared.
Okay, so let's look at some examples of some points from a multivariate normal distribution. So let's fix p equal to 2, so 2 dimensions, so it's a bivariate normal distribution. And I'm going to pick 4 different distributions. Okay, so I'm going to change the mean vector. I'm going to change the covariance matrix. So first of all, the mean vector. I'm going to let the first cloud of points have mean 0, 0. Okay. And the covariance matrix is just going to be the identity. So we get this top left plot here. You can see its mean is 0, 0, the point in the center. And you can see that roughly it has variance 1 in this direction and variance 1 in the y direction. Now I've drawn on top of the plot here confidence ellipses. So this first confidence ellipse contains 66% of the points. The second confidence ellipse contains 95% of the points. The second plot, I've kept the same covariance matrix, so the identity again, but now I've changed the mean to be 1 minus 1. And you can see that all we've done is we've shifted the cloud of points across. So now its mean is at x equals 1 and on the y-axis at minus 1. That's the second component, x2. But you can still see it's got the same variance in the x direction and the y direction. For the third set of points, I'm going to take the mean back to 0, 0. But now I'm going to change the covariance matrix. So I'm going to let it now be 1, 0.05. So what this says is we still have a cloud of points centered around 0, 0, and it still has variance 1 in the x direction, but now its variance in the y direction is 0.05. Okay, so it's shrunk, it's collapsed the cloud down, it's squashed it, if you like. Okay. And so these confidence regions, these circles, well, what were circles in the first two plots, have now become ellipses. These are confidence ellipses, again containing 66% and 95% of the points. So for the fourth example, we've still got a mean of 0, 0, but now I'm going to have a covariance matrix that has diagonal elements 1, and now for the first time we're going to see off-diagonal elements that are not 0. So I've got covariance between the two terms being 0.9. And so what you can see here is we get points that are highly correlated with each other. So we've still got centered around 1, 0, 0. We've still got that the first component has variance 1, and the second component has variance 1, but now they're strongly correlated, and so we have this kind of diagonal cloud of points. Okay, that's because we've got a covariance that is non-zero here. So if you were to tell me x1, I could tell you x2. Or I could tell you something about x2. I couldn't tell you it perfectly. I could tell you something about it. And one of the facts we said before, one of the facts I want to kind of highlight here is that the marginal distributions of this top left and bottom right plots are the same. Okay? So if I just look at the distribution of the x1s in both plots, we get the same. So what I've done here, I've taken those two cloud of points and I've plotted the marginals. So this is the marginal distribution of x1 here. It's just all these points projected just onto the x-axis. So I've plotted the histogram. So the same for these points, and you can see we get the same shape in each case. A Gaussian centered around 0 with variance 1. Similar for the x2 values. If I take all these points and project them onto the y-axis, I get a histogram that looks like this. So centered around 0, variance 1. And the same in both cases. So although these two random samples have the same marginal distributions, their joint distribution is very different. These two cloud of points look very different to each other.
So now let's discuss transformations or linear transformations of the multivariate normal distribution. So let's say let x be a normal random variable, dimension p with mean vector mu and covariance matrix sigma, and let y be a times x plus c, where a is a, let's say, a q by p matrix, and c is a vector of length q. Then, well, y is a linear transformation of the x's, so y is going to be Gaussian. Okay, so we're going to have that y is also multivariate normal, but now it's of dimension q, and its mean gets changed from mu to being a mu plus c, and its variance matrix goes from being sigma to a sigma a transposed. So to prove this, just note that y is multivariate normal if and only if b transposed y is univariate normal for all constant vectors b in RQ, but b transposed y is just b transposed times ax plus c, so that is b transposed a times x plus b transposed c. So this is a vector in Rp. So this is some vector in Rp times x, and because x is multivariate normal, we know that that must be normally distributed, plus a constant, so that's normally distributed, so this is normally distributed. So thus y is multivariate normal, okay, and we saw in chapter 1 that the expected value of y, okay, if we know the expected value of x is mu, so the expected value of y is just going to be a times the expected value of x, which was mu plus c, and the variance of y, well, that is just a times the variance of x, which was sigma a transposed. Okay, so that's straightforward. So I just want to highlight a corollary. And let's say if x is normal with mean 0 and variance matrix equal to the identity matrix, so let's say that's P, then if we let y be the matrix square root of sigma times x plus mu, then y, it follows from the previous kind of result that y is going to be multivariate normal of length P with mean mu and variance matrix sigma. Okay, so that follows straight away. We get sigma to the half identity, sigma to the half transpose, which is just sigma. So this tells us how to generate multivariate normal samples. Yeah, we sample from independent univariate normals, put them all together into a vector, then we transform them by adding the mean and multiplying by the square root of the variance matrix. The converse, if you like, of this corollary, so let's make that be part A. Let's have part B being that if x is normal with mean mu, so let's say length P, mean mu variance matrix sigma, then y, which is the inverse matrix square root of sigma times x minus mu, is multivariate normal, dimension P, mean 0, variance matrix, the identity. Okay, here we're assuming that this is full rank. Let's say assume sigma is full rank so that this inverse exists. Okay.